I will start the class in 4 minutes now.
Okay, sure.
Yeah. You are back from work early today?
Yeah, of course. I just came back.
Yeah, yeah. No, because I remember that you said that around 7 o'clock like you would like to start, right?
Yeah, your voice is breaking.
Hello?
Yeah, now it
Yeah,
is clear. Yeah,
yeah, yeah, okay. Yeah, that's what you said that you wanted to start by 7, right?
yeah, it will be useful because just 5:15 or 5:30 only we start from office. Anyway, cab is
Hmm.
there, but another half an hour it will take. On the way there is an airport, so if
Okay.
any traffic congestion is there, it will be delayed. Anyway, I will reach positively by 6:06. I no issue.
You are from Chennai?
Yeah, native is Tamil Nadu, but actually I am here in Trivandrum, Kerala for last 20 years.
Oh, okay, okay. So you're from, like, you are right now in Kerala, right?
Yeah, yeah, working in ISRO.
ISRO, okay, nice. Actually, everybody will also join a bit late, so it's better that we start a bit late. That will be fine. So you can relax and come at it. Okay?
Again, your I think voice is breaking when you're slightly. Yeah, it will be better. Yeah.
Okay. Okay then. I will start the class now. So, welcome everyone. My name is Rohan Jadhav, and I'm a scholar from IIT Kharagpur, and this is the second interactive live session for the Polymer Reaction Engineering course. We'll be going through some uh, model problems which will help you in solving your assignments, and specifically for assignment 2. So I think that you might have been more familiar with the different types of polymerization modes and what are polymers, and you must have studied in depth about it. So we can proceed with that. So here is the first question. First, we have choose the correct options for the following statement. Statement 1. The polymer molecules are attached to each other in the primary bond and secondary bonding forces such as covalent bond, ionic bond, hydrogen bonding, and van der Waals force, etc. Statement 2. A covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form ions. So, uh, in this, first of all, the first statement is that polymer molecules are attached to each other with primary forces. So, as I explained in my last class also, that carbon-carbon atoms, when they form the covalent bonding, that forms the backbone of the entire polymer structure. So, the backbone itself is your formed by the primary forces. So you can see here in the first diagram right here that the black lines where they are joining, right? This intersection is actually a carbon atom. So when it is joined like this carbon atom is majorly forming the backbone force. And then the second part of the first statement is secondary bonding forces such as covalent bond, ionic bond, hydrogen bonding, and van der Waals forces. So we have the ionic and hydrogen bonding also. So you can see right here that the hydrogen which are present, they are having some interaction with each other from different chains. So that is your hydrogen bonding occurring. So that is the secondary force. So the primary force is your covalent bond, and the secondary force is your hydrogen bond. It can be also van der Waals forces also. then the molecules are maybe they don't have the hydrogen atoms inside them. So it can be that they are connected through van der Waals forces also. And ionic bonding in a similar manner. The statement 2 is a covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form ions. And this is best shown in carbon because since both of them are carbon-carbon atoms, the electronegativities of the two atoms will be very small. Basically, no difference between them, and that is the exact reason why the electron sharing occurs because the entire transfer is not possible. So they share the electrons, and because of that, covalent bonding is formed. So for this, statement one is true, and statement two is also. Next, we have is the correct sequence for the dissociation energy of bonding forces in the polymer structure is covalent bond, ionic bond, hydrogen bonding, dipole forces, and van der Waals forces. So yes, that we can see, as I said, the primary forces forming the backbone of the polymer is the covalent bond. So it will be the strongest, followed by the ionic bonding, where ions are playing a major role. So that is also stronger. That is also stronger. But we compare usually ionic bonds with metallic bonds. So in this case, we can see that any free ions are present in a polymer structure. They will attract other free ions and form a particular bond, and that is the ionic bond. So covalent bond is the strongest, followed by the ionic bond, and then hydrogen bonding. Hydrogen bonding is occurring between chains, and it is not that strong. And this you can see in the first diagram again here itself. These dotted lines show the hydrogen bonding effect, and you can see that the hydrogen bonding with the different chains is giving the orientation of this entire body. So that, and then next comes the dipole forces. The dipole formation which occurs because of the charge distribution differences inside a polymer molecule can form that. But dipole forces are quite weak, which are then followed by the van der Waals forces, which are the weakest. So, so this distribution is true. We'll move on to the next slide. In which type of polymerization, temperature is not easy to control. So we have four options here: solution, suspension, bulk, and emulsion. So you might have already gone through, or maybe sir has already taught you the basics of all these polymerization techniques, and we can already tell that solution polymerization is the type of polymerization where you have a solvent and you mix the initiator or catalyst inside it, and then the monomer is then catalyzed inside the solution, and the formed polymer is soluble in that solvent. Same goes for suspension and emulsion, and then we have the bulk polymerization process. Amongst these, temperature is a big factor, but the one where temperature is not easy to control is bulk polymerization. Why is that? Because in bulk polymerization process, we are aiming for a high yield. And to get a high yield, what happens is that the amount of polymerization for the number of chains we have to carry out is much, much higher. And because of that, the temperature control is not that easy because as more polymer forms, polymer is actually a heat insulator. And because of that, the temperature differences which are created inside the bulk polymerization process are quite difficult to control. I don't have a schematic to make you understand that, but I guess that maybe Sir might have made you understand that much better. Next is for polydispersity index, which statement is or are correct. So in uh, polymers, there are molecular weights. So polymer chains usually have different molecular weights. So example, you have a backbone like this. You have different monomers. These small lines are the monomers, monomeric repeating monomers present on the polymer chain. And you can measure the molecular weight of this polymer chain. Let's say this small group has a weight of 1. So if this small group has a weight of 1, how many units are there? 1, 2, 3, 4, 5, and 6. So the combined weight of this polymeric chain will be 6 units. You can call it 6 units. Okay. So next is that polymers usually are not of like not all chains are regular in nature. Regular in nature means not all polymeric chains will have six monomeric groups repeating themselves like this. It won't be formed of six units. It can be of maybe five units or maybe four units. Or some polymer chain will have maybe seven units also. So that is that is just an example case. But in reality, sometimes what happens is the degree repetition is in the order of millions. So one polymer will be having the unit like a million units, or maybe there is some discrepancy between the number of units present inside the present on the polymeric backbone. So in that case, what happens is that I'm basically explaining the entire molecular weight uh, theory so that we can just we are not straight away jumping to the polydispersity index. I will first explain what are the molecular weights, and then I will explain you what is polydispersity index. Okay, so that is the case. So whenever you are defining the polymer weight with respect to the number of units which are present on top of it, right? Uh, uh, that is the molecular weight of a polymer. Now, the distribution in the molecular weight category is number average molecular weight, weight average molecular weight, and viscosity average molecular weight. These three are the basic ones. There are others also, but we will discuss these three first. So, what happens in number average molecular weight is we are defining the polymer's molecular weight with the number of the chain which is present in the highest order. Example, there are 10 chains. Okay, 10 chains in a polymer. Now there are 10 chains present. One of the chains weight is 60, and that 60 number chain is actually repeated at least six times in this distribution of 10 chains. So in this distribution of 10 chains, six chains have the weight of 60. It means that the chain which is having the number 60 is the most dominating one in this entire distribution of 10 polymers. So the entire weight will be focused on this six chains only. So that's why that distribution is called the number average molecule. You are averaging the entire polymer's weight with respect to those six chains and then counting the other four rows. That entire average will be shifted towards the higher number of the polymer chain, particular polymer chain. Okay. Next, we come to the weight average molecule. Now, what happens in weight average molecular weight is, let's take the same example. You have 10 chains. Now, as I said, the six chains are having 60 molecular weight, but there are let's say three chains, which are having 100 as the molecular weight, individual molecule, 100. So what happens in this case is the weight of these three is much higher than these six present right here. Okay, so it's basically they're balancing each other. So you can say that these three are much higher in weight, so the average of the entire polymer chain will be shifted towards these three. And in that case, that is called the weight average molecule. Okay, so that is how you define the weight average molecular weight and the number average molecular. So polydispersity index is defined as the ratio of the weight average molecular weight divided by the number average. It's the ratio between these two. So with this ratio, what we can tell is that what is the dispersity of the chains, the chains and the distribution of the chains present inside the polymer mixture. Because always the weight average molecular weight of a polymer will always be higher than the number average. Why? Because in a polymer mixture, usually short chains are present in a much higher quantity than the longer ones. So what happens there is these short chains will always dominate. But since the weight of the long chains is much higher than these short chains, weight average molecular weight is always higher than the number average. So when you divide the weight average molecular weight divided by the number average molecular weight, so that will give you your polydispersity index. So first statement is correct. Now, whenever this weight average molecular weight and number average molecular weight is same, it means that the polymer is having all chains of uniform length and all of them are considered for the weight. But this is not at all possible for real polymers because that is a ideal situation. So we cannot achieve that in any kind of polymerization method. We might try to achieve it, but the closest we can come to it is around 95 to 98%. So that is only so this polydispersity index is one for only the monodisperse polymer. Monodisperse polymer means all polymeric chains are equal in length, and it is always greater than one for actual polymers. So this second statement is also correct because in real polymers, what's going to happen is weight average molecular weight will always be higher than the number average molecular weight. We know that. So in real cases, weight average is always higher than number average, and so the polydispersity index will always be higher than one. So it will be 1 point something, or maybe 2 or 3 also includes, like the order of magnitude is higher. It is only is equal to 1 for the monodispersed species, and that is the ideal case of a polymer. I hope I'm still audible and the
Yes.
presentation
Yeah,
is visible.
clear. You're audible.
Okay. Okay. Uh, I'll move on to the next one. Uh, this is a simple one. What
Just
is the
one small clarification.
yeah, yeah.
Sorry to, yeah, this actually just for average molecular weight,
Yes.
weight average, number average. Yeah, when we say number average, it is the number of, it depends upon the number of individual molecules like monomers,
Yes.
which is getting attached to the polymer. Weight
Uh,
average generally adds to that individual monomer weight into the number of monomers together, like
yeah, yeah.
sigma n
Correct, correct.
by sigma ni mi by sigma ni, like that we used to put it that way.
Yeah, yeah. Correct.
You have explained certain specific point into that. I am just having some lack of clarity on that weight average part. That alone,
Oh,
can
okay,
you
okay.
please
Yeah, okay. I'll just explain it to you again. Okay. So imagine that again, let's take the same example for the 10 chains. Okay. So we have to create a distribution for this. Okay. Let's create a distribution for this. In this distribution, this is the let's say the distribution factor or the cumulative frequency, and then here we have uh, the molecular weight. Okay. Example, we have the molecular weight. This is the frequency, or you can say the fraction. This is the fraction. Okay, fraction. So the polymer distribution looks something like this. Okay, and on this curve, the number average molecular weight is present somewhere here. So this portion is called NN. Why? Because this is the number average molecular, and weight average molecular weight lies in front of it. So you can clearly see that number average lies before and weight average lies in the front. This is NW. Okay. So how we define the weight average is that weight average molecular weight is defined as the average taken from the point of view of the heaviest chains. Okay. The chains which are the heaviest, when you derive the molecular weight from that point of view, that is your weight average. And number average molecular weight is when you are taking the average from the point of view of the chain which is present in the maximum number in that polymer group. It's like,
Okay,
uh,
so more
yes,
more like if you are having multiple chains, small and big,
yeah,
number average will dominate with a smaller number of chains, multiple, which is more.
yeah, yeah,
Weight average, even if it is a bigger, if it is having higher molecular weight, will consider that for weight average evaluation.
yes, exactly. So the thing is,
Okay, clear.
yeah, all polymer mixtures will have number average also, weight average also. Okay, so that is one. The
Yeah,
third
yeah.
one, yeah, the third one which I talked about was the viscosity average, and it lies somewhere in the middle of these two. Now, how viscosity average is defined as when every polymer is soluble in some sort of solvent. Okay, so whenever that polymer is added into that solvent, the polymer chains, right, they dissolve and they open, and that will increase the viscosity of that solvent. Now, what you do is you measure the same amount, like you measure the viscosity of the solvent when it is present in its native state without any polymer, and measure it when it is present with the polymer, with the increased viscosity. This difference in viscosity, it will give you a measure of the molecular weight, and that lies in between the Mn and Mw. That is called the Mg, viscosity average molecular. Uh, to determine the molecular weight, usually the one instrument which is used is gel permeation chromatograph. Okay, so this is the process which is used, and in that instrument, what we do is we dissolve the polymer in some solvent and then pass it through a gel column. And in that gel column, the chains which are heavier in weight are retained and which are lighter. Sorry, the ones which are heavier are passed through first, and which the ones which are lighter get stuck inside the gel pores of the column. And with that, you will get a distribution which will give you the determination of all the molecular. So that was just some extra information. Maybe it won't be that much relevant for you, but that was just some extra information regarding the point. Moving on to the next question.
Yeah, clear.
Yeah. What are the other classifications of suspension polymerization? We have bead polymerization, powder polymerization, and emulsion polymerization. I guess this is a very straightforward question. So suspension polymerization's other classifications are bead and powder polymerization. You might have already, I think, seen in the course itself, and it's present in the course notes also, how the bead polymerization forms. Whenever the monomer polymerizes and the polymer is present as a perfect bead and it separates out as a perfect bead is called the bead polymerization. And in case of powder polymerization, whenever it's not separating as a perfect bead and it is present as small molecules is called the powder polymerization. And they are like just the parts of suspension. So these two are the correct answer for this question. Moving on. The polymer synthesized by suspension polymerization process among the following is polystyrene, styrene butadiene rubber, nitrile rubbers, vinyl acetate, homopolymer, and copolymer. So in this, polystyrene is the one which is prepared by the suspension polymerization. So I have given the reaction for the polystyrene uh, suspension polymerization. Basically, it goes in the initiation, propagation, and termination steps like we discussed in the last class. These kinds of questions are more like, what should I say? You'll have to read about them and only then you will get to figure it out. There are different kind of questions where somewhere you have to apply the scientific concept, and in some cases you'll have to just maybe remember all these parts. So here you can see that how the styrene molecule is present, and then there is a radical. The radical initiates the makes the initiation step. It attaches, and then we have a free lone pair right here. And then because of the propagation, it attaches to the other molecules, also styrene molecules. And then you have the uh, polymer chain forming. And then the termination occurs when two free pairs come together, and then they terminate the reaction. So the chain is complete. So polystyrene is the one which is produced by the suspension polymer. Styrene butadiene rubber is produced by emulsion polymerization and solution polymerization. Moving on, which is incorrect for the suspension polymerization process. It is there are four options. It is carried out in continuous stirred batch reactor. Initially, the monomers are dispersed in continuous liquid phase with agitator. The spherical polymer particles formed are in the range of 50 to 500 micrometers. And fourth is the control of the particle size distribution is not an important issue in this process. So for suspension polymerization, definitely the incorrect answer for this, we can clearly see that control of particle size distribution is not an important issue is the answer for this, because definitely the size of the bead or how the polymer molecule is forming is of utmost importance. So again, you can answer these questions quite easily by just reading the process description and what are the parameters involved in the process. So the learning about the process parameters of every polymerization process can suffice to answer such questions. Moving on, we have Which one of the following properties of polymer is desirable during the synthesis of polymer? Now, this is the question where it is important to know the concept of the polymers. So first we have the low molecular. Now, if your polymer is having low molecular weight, definitely it will have lesser viscosity. So it will become much more handleable during the synthesis of any kind of polymer. So that is the correct answer. Next is impurities. If any impurities are present inside the polymer, what would that do? It will basically stop or hinder the synthesis of the polymer. So that is undesirable. Next, we have the low viscosity. Now, low viscosity of a polymer is basically, as I said, the first point and the third point are quite synonymous. So I would say that low viscosity of a polymer is very important because handling of the newly formed polymers is quite a difficult task sometimes. And because of that, also heat fluctuations can occur because as polymers form, polymers are basically thermal insulators. So to control the temperature of the reaction or maybe how the polymerization process is going on, the rate at which the polymerization reaction is occurring is also difficult to control. So that's why low viscosity is quite important, but the molecular weight part might not be correct all the time. Why? Because maybe you want to manufacture a polymer with higher molecular weight and maybe somehow during the synthesis you would want a low viscosity. But this can be achieved by dissolving the higher molecular weight polymer in some sort of solution. So basically you go for something called solution polymerization in that case. So low viscosity would be the correct answer because impurities is definitely not an answer for desirable desirable parameter for the synthesis of the polymer. And lower molecular weight is quite subjective. It depends on the application for which you are manufacturing the polymer. It might be lower, it might be higher, so it depends on it. But one thing which everybody would want during the synthesis would be the low viscosity. So low viscosity is the correct answer. Now we have the completely amorphous polymers show only the glass transition temperature. Next, crystalline polymer show T melting temperature and semi-crystalline polymer exhibits both temperature. So it is asking us what is true and what is false. So so we have two graphs here. I've given you there are two graphs I put here. First graph is actually showing the relation of temperature with the stiffness or the modulus of the polymer. In next graph we have the temperature and the heat flow. So the second graph is actually a scan from a machine called or the process called differential scanning calorimetry. So what happens in differential scanning calorimetry is that you are able to identify the phases through which a polymer or a material goes before deforming. I will explain the second graph later. I'll explain the first graph first. So we have completely amorphous polymers show only the TG, glass transition temperature. Now, here we are encountering a term called glass transition temperature. Now, what is glass transition temperature? The name itself suggests that glass transition temperature. So what is glass? We have the silica. Silica, when it is heated up, it forms glass. All the sand and glass. So glass is first of all extremely brittle. So that is called the glass one. It's example it's extremely brittle. So the brittleness of a material is shown by its glass transition temperature. If a material's glass transition temperature is very low, uh, if the glass transition temperature of the material is quite high, it is not going to transition from its glassy state to the rubbery state with the increase of temperature easily. It means that the material will stay brittle. So, for example, glass itself doesn't melt quickly with temperature, and it stays glassy. Glassy in the sense like it's brittle, and it is not able to. It's not that flexible. When you heat polymers, they become flexible, and they start to flow also. So that's why the modulus or the stiffness decreases as the temperature increases. And the first transition which occurs is called the glass transition. It leaves its glassy or the brittle state and goes to the rubbery state. This temperature is called TG. Means that is called the glass temperature. So completely amorphous polymers only show glass transition temperature. Now, what is the meaning of amorphous polymers? That amorphous polymers are the polymers which are not ordered correctly. Ordered correctly in the sense like polymers, whenever they are synthesized, they attain a certain arrangement, and that kind of arrangement decides what are its properties. Basically. Will it be more crystalline in nature or amorphous in nature? Now, amorphous in nature means that the polymer chains are not ordered in any particular order. And because of this disorder, what is going to happen is the polymer chains might not have the high mechanical strength. Only crystalline materials will have high mechanical strength in them because the polymer chains are correctly ordered. This ordering allows the polymer chains to pack with each other more densely. So you can clearly tell from the name density itself that you can correlate it with the LDPE and HDPE example. So LDPE chains have slight branching in it. And because of that branching, the close packing is not possible. And because of that, it's not as dense. It will have more amorphous regions in it. Whereas high density polymers have less branching. Because of that, there is something called close packing. And because of that, the crystallinity measure of that polymer, HDPE, will be much higher than the LDPE. So in that case, it will the amorphous polymers will show TG and crystalline polymers will show melting temperature. Why they will show? Now we come to crystalline polymers. Now why crystalline polymers show melting temperature is that when crystalline polymers are heated, because of the close packing, they are able to actually resist the temperature changes quite easily. And they don't flow very quickly because since they are closely packed, the interactions between each polymer chain are quite prominent. Whereas, like compared to the case of amorphous polymers. In amorphous polymers, since there is no close packing, the chains are quite far apart and they are arranged in haphazard. And because of that, the amorphous polymers are not closely packed. In crystalline polymer, since they are closely packed, the secondary forces, for example, hydrogen bonding or any other force, is acting much more efficiently. And because of that, it is able to resist the temperature change much more efficiently. And as the temperature increases further, only melting occurs. Why melting occurs is that the temperature itself overcomes the secondary forces and the chains will start slipping past each other. And when that happens, the polymer starts flowing, and that brings us to the rubbery flow or the rubbery state. So crystalline polymers will straight away go to the rubbery flow or rubbery state if and only if it's a thermoplastic polymer. Again, going back to the first class, as I explained that thermoplastics and thermosettings, how they are differentiated is that thermosettings are basically interlocked or interconnected through cross-link. And since cross-linking is another backbone bonding, that is much more stronger than any kind of secondary interactions. So that makes them even more harder to reform under high temperatures. And the third part of the statement is semi-crystalline polymer exhibits both temperatures. Now, the word here is semi-crystalline. The one statement I will tell you now is that all polymers are semi-crystalline. Semi-crystalline means having both uh, parts of amorphous and crystalline. And polymers can have either crystalline structure in a much greater range and amorphous and smaller, or amorphous in much greater range and crystalline as well. But no polymer can be 100% crystalline. If it was 100% crystalline, it definitely wouldn't be a polymer. Because the thing which separates polymer from other materials is that it is moldable and it can be molded and deformed with use of temperature easily. So that differentiates polymer from other materials. That's the exact reason. And that is why polymers don't exhibit 100% crystallinity. They exhibit semi-crystalline. Means some portions will be amorphous, maybe a major chunk will be crystalline. So semi-crystalline polymers exhibits both temperature. So that's why all polymers will show a TG and they will show a melting point. But crystalline polymers, that is, maybe a material is almost 70 to 80% crystalline, its melting temperature will be much more prominent than its glass transition temperature. But always remember this, that almost all polymers are semi-crystalline. So now I will explain you what is the second type. Now the technique which has been used here is called the differential scattering calorimetry. Now what is the meaning calorimetry tell you is that whenever you burn something, you are burning it with respect to the calories which it has. Similarly, when heat or temperature is passed through something, how much heat is flowing through that body will give you the calorific value of that material. Okay. So in differential scanning calorimetry, what you do is one, you always compare the unknown material, which is your polymer or any other material, with a known material. Now, the known material is maybe a metal, which we exactly know how the heat flows through it and what is the amount of heat flow through. So you can see here there is on the x-axis temperature and on the y-axis we have heat flow. That is milliwatt. Okay. So what is happening here is that as the temperature increases, heat starts flowing inside the material. Now, the moment the glass transition is encountered, you can see that the drop is there. And again, here we have a drop. So when the polymer deforms, it is basically uh, what what should I say? It is basically undergoing change because of the heat which is being applied. And since it is undergoing change, heat is flowing through. And since the heat is flowing through it, it is absorbing that heat. And that is the exact reason why the temperature goes down. It goes in a negative point because it is absorbing that heat. So it becomes endothermic in that case. Okay. It is absorbing that heat and then it flows. Starts flowing. Slightly it will flow. And then as it goes inside, you can see that the entire polymer will then melt away and then start flowing. Once it starts flowing, convection can occur. Clearly, convection can occur, and then it will release that heat. It will totally release that heat. Glass transition, you can see that as the temperature goes to glass transition, next we have the rubbery flow. And that rubbery flow comes in during uh, when it goes under any kind of melting or any different like any kind of other phase change. Here also, when the peak comes in, crystallization occurs. Crystallization temperature is the temperature where the ordered crystalline structure of the polymer is disturbed. Entirely it gets disturbed. So you can see that in the glass transition temperature, here the decline shows a transition from the glassy state to slight movement. The polymer might become soft and it's becoming weaker. And as further it goes, we encounter crystallization. And the moment the crystallization occurs, all the crystalline portion of the polymer starts subsiding and all the polymer starts flowing. And then all the energy is given to melt. The entire polymer starts flowing. So this statement that is completely amorphous polymer shows only glass transition temperature, crystalline shows melting point, and semi-crystalline exhibit both is true. So the answer for this question is true. Sorry I took so much time on this question because it was very important for me to make you understand how these three regions work and how these things happen. I guess you
Yeah,
might have some doubt.
I have some small clarification.
Yeah.
This TG and melting
Hmm.
both requires a heat. Probably TG will not induce any phase change, but
Yeah.
melting may
Yes,
induce
yes, yes.
phase change. So
Yeah.
both will absorb the heat, so heat can go negative. And in case of crystallization,
Hmm.
we are seeing in the positive side because
Yeah.
there the crystal start forming and growing, but that is directly relevant. Okay, polymer side, if you are seeing the alignment of the chains,
Hmm.
uh,
Yes. Uh,
that is
yeah, yeah. Actually, I would like to add one thing. Crystallization temperature is never correctly shown in the starting scan of a material. This is actually the starting scan of the material. There is another scan which occurs when you're cooling the material. When you cool the material, at that point again you see a crystallization. And that temperature is the real crystallization. Why? Crystallization process occurs when you cool down a polymer. So when you're cooling down the polymer chains have time to come back together. And once they come back together, they arrange themselves and pack themselves into a crystalline fashion. That is what is called the crystallization process.
Okay. My
Yeah.
question is whether it should be the crystallization. Why it is showing positive? Like heat flow is on the positive side.
Okay. Another thing I'll add to this thing is that heat flow shown in a differential scanning calorimetry can either be shown by exothermic heat or endothermic. So this scan I would say is present in endothermic heat scan. If it was an exothermic heat scan, you will see that the glass transition will be rising up, crystallization will be going down, and melting will be up. So it depends. What is your scanning mode? Okay. So in that kind of scanning mode, you will see that the the graph will be basically inverted. Okay. So don't
Okay, fine,
confuse with that.
fine.
Okay. So don't get confused with that because if I show you the other side of that graph, that is the exothermic or endothermic, the same graph will be inverted. These points will remain the same. It's just that they will be inverted. Melting will be on top, crystallization will be down, glass transition will be top, something like that. Okay. So it
Okay, clear,
depends. It depends on what kind of heat your machine is trying to measure. Fine.
clear, clear. Yeah.
Yeah. So have you gone through the second assignment or the third assignment yet? Have you seen the questions?
Second is submitted. Third, I am yet to start because actually one more course also barely going in. Total four courses I am attending this
Oh,
time.
okay. 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 So
So
you're
probably
attending
third
four
assignment
classes.
I am yet to start.
Oh, okay. Okay. Okay.
That is,
Okay.
I
So
think, loaded yesterday only. Uh,
yes, yes. Third one has been loaded yesterday only. So yeah, that's what I was thinking that like, shall I give you more questions? Okay, let's see one like because this part is actually still yet to be taught by sir. So I would suggest that we not take a look at this because I would say the submission date for the assignment 3 is when?
for this week, it will be for next Wednesday.
Next
For
Wednesday,
last 2 weeks, the submission date is tomorrow.
tomorrow. Okay,
There is one
last.
week gap. So last 2 weeks, it will be tomorrow last date.
Huh.
This week will for this week's assignment, it is next Wednesday, coming Wednesday. That is 14th.
Okay, 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 okay. Then I would say I think still the reaction kinetics and all are the things which sir hasn't taught you. Has sir taught the reaction kinetics and stuff like that?
Yes, currently now ended up with the type of reactors, like different types of reactors and controls only. Mostly on
Okay.
control part only it was there,
Hmm.
and type of control also, like that much only it was covered in this. That the third
Okay.
week session I
Okay.
am yet to go through.
Okay. Okay. Yeah. Yeah. So I think he has still yet to teach you about the chemical kinetics. So I would suggest that we stop right here because that this is a very good place to stop because I guess this much will help you how to answer the second assignment, third assignment.
Exactly. Yeah.
Because these
Yeah.
assignments are, I would say that only in the introductory phase. As we go further, things will get more complex, and at that time, it will be better to prolong this and have a better discussion. Okay.
Okay. Now for subsequent questions are not relevant to maybe this week subjects, this week
Like
classes.
if it's
Like,
more about reaction
okay, okay.
kinetics.
This
Yeah, yeah.
okay.
So
That is it to be another
yeah,
element.
yeah,
Okay, okay,
exactly.
okay. That's fine.
All these
Yeah.
things are
Okay.
related to reaction
These are yet
kinetics.
to be.
Yes, yes.
Yeah.
These are yet to be
Yeah,
covered.
yet to be covered. Yeah. Fine.
Yeah. Like if you want, I can teach you them, but it's like you haven't been exposed to it yet, so it's better
Yeah.
not to do that, right?
Yeah. Exactly. It is better that we will go through the classes and understand
Hmm.
both that.
Yeah, that will be much
Yeah.
better. Okay, so If you have any other
Yeah.
doubts, or if you want me to like brush up on any other concept you might be lacking in, or you might be interested in, you can tell me, and I can come back in the next class and tell you about that.
Uh, uh, no, sorry, pardon, I am unable to get it clearly.
And I said that if you have any doubts, or if you want me to take up any other type of concept in polymer engineering itself, I can help you
Okay,
with that.
okay.
Yeah.
Yeah, actually, now with respect to the polymerization process, yes, it is clear. Like the different types of polymerization routes,
Yeah.
whatever discussed is very elaborate. Whatever the professor has given, it is very elaborate, and that is good enough. We can easily understand. But
Okay.
when it comes to probably the kinetics and the anyway control, also it is only an introduction part. What sir
Yes.
has
Yes.
given, like fully, it is not. It is
Okay.
Pro- Probably we are yet to get into that full part of it. Only the beginning of it only was given, a beginning introduction part.
Hmm.
Maybe the subsequent sessions, I think more clarifications will be there. But only to just to confirm, now
Hmm.
say final exam will be with the MCQ, if I believe correct, if it is correct.
Yes.
Uh, and what will be the like time schedule will be there, because since I am new for this, I am yet to understand. That's why I just want to prepare now itself how it will be like overall, like it will be like the duration, total duration, and how many questions overall, how
Uh,
it will be the questions.
Durations of the course or the test?
Test, final exam.
Okay, final exams duration will be like around, it will go on for, I think, 1.5 hours or 2 hours. It's somewhere around
Okay, okay.
that. And all questions will be
And
MCQ based. Definitely problems will
okay,
come. Numerical based
okay,
problems will
okay.
be
But
there, I guess. Hmm.
yeah, probably that the type of problems is there, then it will be really helpful, because when professor is going through his lecture, it is more of like descriptive. We are to go through any type of problem. So if at
Hmm.
all any problem is there, then it is given in this what we can say, like weekly classes, it will be really helpful.
Yeah, yeah. Actually, I think the questions for this course, the final one will be like it won't have that much in-depth numerical problems. They will be like small problems only, but not that much in-depth.
Okay,
Okay.
okay,
I
okay,
suggest that
okay,
you still go through the descriptive parts and all those things. That will be much better. Okay.
okay, okay. Fine, 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 fine.
Hmm.
Thank you.
Yeah.
If,
So,
if that is the case, accordingly we can prepare. I have taken this RM as well as our this MATLAB also as a part of my compulsory coursework for my PhD. Uh,
oh, okay, okay.
so
You're
plus
doing,
this one, yeah, yeah, I have just joined in our institute, IAST, Indian Institute of Space Science and Technology, for PhD coursework. There actually now, since work is there parallelly, I have an option to complete this course through NPTL, so that that will be there as part of my coursework. That will be recognized, getting recognized. That's why.
okay, okay. I get it. I get it. So you are working in ISRO right now?
Yeah, yeah, I'm there for last 20 years. 2003, I joined. Almost 21 years.
Okay. If you don't mind me asking, what's your course or what you're doing?
Pardon, sir?
Uh, like, if you don't mind me asking, what is your post, or which
Yeah,
field you are working?
yeah, currently, earlier I was there in the propellant area, that is solid propellant area. Now I am in liquid propellant. So currently I am holding a division as a deputy general manager.
Oh, okay, okay. General manager, deputy
Yeah,
general
deputy.
manager. Okay,
Yeah, yeah.
okay, okay. Wow, that's it. Congratulations to you. Just saying that because it's such a good thing.
Thank you. Anyway, actually, this is one area I can refresh all the things. Though chemical engineering is my background,
Yeah.
but in MTech I could go through the what we can say, like a polymer part also, but still it is more than 15 years. So it is good that I got everything refreshed, so that it will be giving additional information also on the latest in this area.
Okay.
So I really enjoy getting this information because once the lectures I am hearing, I could refresh everything.
Okay,
That way it
nice.
is very useful.
I'm actually really helpful that I'm able to help you like brush up any of the concepts because I think you guys are doing great job and thank you very much for that.
Sure, sure. Anyway, it is part of teamwork. I am handling only one area where it is liquid propellants are there. So there are different areas are there, and definitely it is a good teamwork. For
Okay,
yeah.
okay, okay, that's great.
Thank you,
So
thank you,
like
thank you.
if I want to ask you maybe something else also about this, so like can you give me a contact or something? I'll just write it down.
Yeah, shall I share in your direct?
Chat box. Yeah, yeah, just type
Yeah.
it in the chat box, I guess. I'll just take your
Okay.
contact.
Okay.
Yeah.
Yeah. Yeah.
Oh, okay. Thanks a lot. Thanks a lot.
Welcome.
Yeah.
So,
Uh,
so shall I? Yeah. Is it continuing further, or shall I?
no, no, it's fine. You can leave.
Okay.
You
Okay.
can.
Thank you. Thank you.
Yeah.
Thank you so much. Thank you. Thank you.
Thank you. Thanks a lot. Yeah. Uh, I guess you have joined right now, so I'll just go through the questions once more. Uh, I'll just go through the questions once more. My name is Rohan, and I'm the TA for the Polymer Reaction Engineering Interactive Live Sessions. I'll be showing you a few questions which will be helpful for you to solve your uh, assignment problems. So, starting from the first one, we have choose the correct options for the following statement. Statement one is the polymer molecules are attached to each other with the primary and secondary bonding forces. So, this covalent bond, ionic bond, hydrogen bonding, and van der Waals forces, etc. Statement 2, we have covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form ions. So we can clearly see that polymer molecules are formed with a particular polymer chain backbone, and that polymer chain backbone is having uh, the molecules which are attached to each other are attached to covalent bond. So the primary forces are the covalent bond. Next, we have the secondary bonding forces such as hydrogen bonding and van der Waals force. So here itself, you can see in the diagram that there are hydrogen atoms present and the dotted line shows the hydrogen bond. Since they are not directly connected, these two polymer chains, that is called the secondary bonding force. And this one is the primary bonding force. So statement one is true. Statement two, we have a covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form ions. So we have two carbon atoms present here, and when they join together, uh, you can see that the electronegativities of both carbon atoms are quite low. And since there is no difference between them, proper electron transfer is not going to happen, and they end up sharing the electrons, and that sharing forms the covalent bond. So that's why statement one is true and statement two is also. Next, we have the correct sequence for dissociation energy of bonding forces in polymer structure is first, we have the covalent bond, next, we have the ionic bond, and then we have the hydrogen bonding, dipole forces, and van der Waals forces. So, as I said, in polymer chains, the backbone, basically the polymer backbone is formed by the covalent bond. And because of that covalent bonding, what happens is it is the strongest bond holding together the polymer chain. So, dissociation of that polymer, that bond is the most difficult and it takes the highest energy. That's why covalent bonds dissociation force will be the highest, followed by the ionic bonding and the hydrogen bonding and dipole forces and van der Waals forces. So this statement, which shows this distribution, is also true. In which type of polymerization, temperature is not easy to control. So you can see that in all of these polymerization processes, uh, that solution, the one we have where the temperature is not easy to control is the bulk polymerization process. Why that happens is in bulk polymerization process, the rate of polymerization and the quantity which is being operated upon is quite high. So as the polymer forms in a higher quantity, And since polymer is a thermal insulator, the heat accumulation because of that is very high and the temperature control is not easy. In emulsion and suspension, it is quite easy to control, and in solution, the entire polymer itself is soluble in a solvent. So there it becomes much more easier as the heat transfer inside the solvent occurs, and that itself can be done quite efficiently. So bulk polymerization is the answer for this question. Next, we have for polydispersity index, which statement is correct. We have four statements here. So the first we need to know what is the weight average molecular weight and the number average molecular weight. Number average molecular weight of a polymer is defined when we are taking the molecular weight average with respect to the number of chains which are present in the highest amount. For example, if you have 10 chains and the number of 10 chains and there is one chain in that which is having the molecular weight of 6, and that chain is present at the highest amount in that distribution of 10 chains. So the entire average molecular weight, when it's focused from that point, is called the number average molecular. And when it is focused on the weight average molecular weight, you are going to look at the chain which is having the highest weight. It doesn't matter in how many numbers it is present, it should be having the highest weight. Then it gives you the estimate of weight average molecular. So the ratio between the weight average molecular weight to the number average molecular weight is the polydispersity index. That is weight average divided by number average, it gives you the polydispersity index. When weight average molecular weight and number average molecular weight are same, the dispersity of a polymer is uh, is equal to 1 for monodisperse polymers. In monodisperse polymers, it's ideal polymer and all chains are present, all chains are of equal length. Okay, all chains are of equal length. And that's why the polydispersity index is equal to 1. And for uh, and if it's greater than 1, that is a real polymer. Because in real polymer, all these polymerization processes cannot account for the entire chain. We cannot account that we cannot account for the uniformity of all the chains. And why is that happening? Is because of course there are n number of parameters which affect the polymerization reaction, and because of that, some chains can be longer, some can be shorter, and all these things. So first one is ratio of weight average molecular weight to number average molecular weight, and next we have the is usually of the monodisperse polymer greater than for actual polymer. These two statements are correct. Next, we have what are the other classifications of suspension polymerization. Suspension polymer. So this is a very straightforward answer. For this, we have the bead polymerization and powder polymerization is the correct answer because these two are the different forms of the suspension polymerization. As you know, bead polymerization, what happens is the monomers polymerize and the polymer globule which forms is in a perfect bead-like structure. So that is the bead polymerization process. And in powder polymerization process, when uh, the globules formed are not in the perfect bead shape and they are dispersed throughout, that is called the powder polymerization. Next, again, is the more of an process related question, manufacturing process related question. Polymer synthesized by suspension polymerization process among the polymers. So among these, we have the polystyrene, which is synthesized by the suspension polymerization. We have initiation, propagation, and termination reaction going on for the polymerization, polystyrene's polymerization process by the suspension polymerization reaction. Next, we have which is incorrect for the suspension polymerization process. So again, this is related to the process parameters of the suspension polymerization process, that the control of the particle size distribution is not an important issue in this process is the incorrect one among these three. As you can see, it is carried out in a continuous stirred batch reactor. So here is a suspension polymerization setup, and you can clearly see that this is a CSTR or continuous stirred batch reactor. Next, we have the initially the monomers are dispersed in continuous liquid phase. So the liquid phase is present. Liquid phase can be water or anything else. With an agitator, we have an agitator and it is mixed fluid, and then we have the continuous liquid phase. Then we have the spherical polymer particles formed are in the range of 50 to 500 micrometers. 50 to 500 micrometers. This is quite a subjective statement as and the uh, distribution can lie in quite a high range of this 50 to 500. So this is also correct. But the control of particle size distribution is not an important issue in this process is the false state. Which one of the following properties of the polymer is desirable during the synthesis of polymer? So let's go through them one by one. Lower molecular weight is definitely uh, quite like it's like a very surface level statement that you want to have a low molecular weight polymer. You can either have low or higher molecular weight depending on your application. Impurities are totally not desirable, so that is also incorrect. And then we have low viscosity. Low viscosity is very much desired during the synthesis of polymer because during the synthesis, the handling of the polymer is to be done quite efficiently, and that's why low viscosity is preferred. So low viscosity is the correct answer for that question. Completely amorphous polymers show only glass transition temperature. Crystalline polymers show melting temperature, and semi-crystalline polymers are exhibiting both. So what's happening in this case is that uh, in amorphous polymers, what happens is the polymer chains are not arranged in a proper densely packed matrix, and because of that, it is an amorphous polymer. In crystalline polymers, the polymer chains are closely packed together with each other, because of which what happens is the molecular interactions are on a much closer scale and they are more tightly packed. And then we have the semi-crystalline polymer, which has both the phases of amorphous and the crystalline polymer. So amorphous polymers definitely, since they are not at all closely arranged, they show the uh, prominent glass transition temperature. Glass transition temperature means when the polymer goes from its brittle state to the rubbery or the melting state, rubbery state. So that is called the glass transition temperature. Crystalline polymers, when they are heated up, what happens is that it starts to melt, and because of that melting, it will change its phase to liquid, or it will become a molten polymer, and there is viscous flow initially. So that is more prominent in the crystalline polymers compared to amorphous polymers. In semi-crystalline polymers will exhibit both these, and all polymers are basically semi-crystalline in nature. All polymers are semi-crystalline in nature except the ones which have also been cross-linked. So then they won't be showing these to temperature. So in that case, it is true. This statement is also. So the next questions, we'll be taking a look at those next questions in the next class because that is still not pertinent to you because sir hasn't started the chemical kinetics reaction of the polymer reaction process. So it will be better if we had come to the next class. But for solving the current assignments, these many questions are more than enough. So if you have any doubts or if you want me to clarify any concept or anything, you can ask me. Or else this class is over. Or yeah, all the questions are over. And if you have any doubts, you can ask. Hello. If you don't have any doubts, then yes, you can exit. And this interaction video will be uploaded on YouTube. And this PPT will be available as notes for you to see through. Like the entire session will be available for you to see on YouTube itself. So you can go through that and take a look at the discussion which I just did an hour back with the previous videos. So that will be much. Hello, if you are not you're not going to respond, then I told to end the meeting or something like that. Okay, then I will wait for some more time and then maybe we can wrap it up and then